Hello scholars, this is our last unit. This video is going to be a little longer, so hang on, it'll be worth it. Alright, let's read it. It's 3 pages. Here's the first one. The chemical equation for the hydrochloric acid and zinc reaction is shown below. So we got HCl, that's hydrochloric, and zinc goes to zinc chloride and hydrogen gas. Okay, what does this say? Reactants, yeah, these are the reactants, these are the products. Used up, consumed, disappear, quantities decrease, mass or pressure decreases. So these are getting used. They're going away. Alright, going away. And then these ones are made, are produced, appear, quantities increase. So these ones are getting made. Okay, note that as the chemical reaction is carried out, the reactants are used up. They react away, whereas the products are made, they're produced. Chemists use this to describe the rate of a reaction. Okay, that's key, rate of a reaction, or how fast the reaction goes. So that's how fast. For example, zinc metal can be dropped into concentrated or dilute, that's the opposite of concentrated, hydrochloric acid. So concentrated means lots of HCl. Dilute means few HCl. The reaction occurs much more quickly in concentrated acid. If a reaction ever occurs in the opposite direction, it's said to be the reverse reaction. Okay, so if the reaction's occurring more quickly, that means more reactants used. What's this? So dilute, this one's slow. See how it's a smaller balloon? This one's a bigger one. Well, it's producing hydrogen, which is gas. So this one is producing hydrogen faster. So it's getting more product faster. It's using reactant faster. So that's how they measure rate of reaction. Oh, we're not done. How would a chemist justify that the reaction on the right is faster? Using the words from the example above, you might say any one of the following things. I know the reaction on the right is faster because H2 bubbles are formed more quickly, right? That's the product. The zinc metal disappears at a faster rate. That's a reactant. It's disappearing. The reaction with concentrated acid is faster since the quantity of zinc chloride increases more quickly. So that's because it's a product, it's increasing. And quickly means it's faster. Okay, makes sense. What's next? Ooh. For a reaction to occur, the reactant particles must collide. Why is everything always colliding? I swear, chemistry is so violent. Okay, they've got to collide with enough energy, okay, that's important, cause reactant bonds to break and product bonds to form. This energy is the activation energy. So that is the energy needed when colliding. In addition, the reactant particles must collide in the correct orientation with one another. And orientation is like direction. Some people talk about sexual orientation, like do you like guys, do you like girls? It's which way are you pointing, I guess. Orientation. So they have to hit in the right way. When this happens, the reactant particles are able to form a temporary arrangement called an activated complex, which facilitates bond breaking and making. These activated complex, they don't last long. So don't last long. Like milliseconds, microseconds, then they break apart. But you've got to have the activation energy to get there. So for reaction to occur, the reactant particles must collide in the correct orientation and with enough energy. If they do not, they will bounce apart and products will not be formed. Various factors can increase the frequency of collisions between particles and the energy of the collisions. These factors will speed up a reaction. This is very similar to rate of solution. So I mean, let's think about those. Temperature, that was one. Surface area, agitation, pressure for gases, pressure for gases. These are all going to have an effect on the rate of reaction, and you should be able to reason it out based on the fact that the more collisions, the faster it's going to go. What's this say? Enough energy but incorrect orientation. So they're not pointed the right way, nothing happens. Okay, they're pointed the right way but not enough energy, nothing happens. They have enough energy and they're pointed the right way? Oh, look, they made something new, right? Started at that, ended at that. Alright, okay. Last page, catalysts. What's going on in this diagram? Look at this diagram. Potential energy, that's like the bonds. Reaction progress. Exothermic, I know exo means it's giving energy. Endo is taking. So what's happening? Energy released, well yeah, that would be exothermic. Okay, so the products have less, so they're going down in energy. But look at this, it goes up in energy first, that's the activation energy. I see the same thing happening here, activation energy, but this one's bigger. And the products end with more energy, so there's a net absorption. So here it absorbs energy, but then it goes down. So it's exothermic. Okay, reactions either absorb or release energy. Yeah, absorbs, endo, release is exo. Reactions that release energy are called exothermic. I know, I just told you that. And the products have less energy than the reactants. Products have less energy, right, because they lost energy. Endothermic reactions absorb energy, and the products have more energy than the reactants. Yes, because they absorbed energy, so of course they're going to have more. Although there are these two types of reactions, see how I just restarted reading it? Sometimes you got to do that. They both require energy to start. This energy is called the activation energy. So this is the energy needed to start, and is sometimes abbreviated EA. Activation energy is why the gasoline in fuel tanks doesn't explode unless there's a spark or flame. So the spark or flame is the activation energy. When your car battery is dead, you can't provide the activation energy to the engine, and so the combustion reaction that powers your car won't start. Okay, last slide. A catalyst is often used to speed up a reaction. Okay, so this is another way to speed a reaction. Catalysts lower the activation energy, which makes the reaction need less energy to get started. As a result, more reactants are able to react and the reaction goes faster, creating more products. One example of a use of catalysts is in the catalytic converter. Okay, hold on, let me read this again. So they need less energy to get started, and so more react and it goes faster. And this is just showing that, yeah, they need less energy if there's a catalyst. But the reactants and products are still the same energy. And so like the delta H, this is still the same amount of exothermic. It's just going to go faster because it needs less to get started. Okay, one example of use of catalysts in a catalytic converter in cars. Exhaust gases containing harmful pollutants are passed through catalysts that help convert the pollutants to less harmful chemicals. The reaction would not occur quickly enough without the catalysts. So I guess this helps decrease smog. Huh, okay. Well, make sure you have key points and questions for all pages 1 through 3. At the very top of page 1, that's a demonstration. We'll do that in class. So I'll see you in class.